Module 9, Lecture A, Clustering Concepts. By the end of this lecture, you will be able to describe clustering as grouping similar examples based on feature values. Use simple distance-based reasoning to decide which examples belong together, and interpret clusters in terms of meaningful patterns in a given context. Clustering without labels. No target column. In clustering, there is no target column that tells us the correct group for each example, unlike tasks such as predicting house prices or diagnosing diseases. We only have the feature values for each example and no labels that say Group A or Group B. The clustering algorithm must therefore discover structure on its own by examining these features. Its goal is to find patterns and group together examples that are similar, without any predefined labels to guide it. In clustering, there is no target column or predefined labels, so we cannot directly compare the model's output to a known correct answer. Instead, the algorithm groups data points, such as customers with similar ages and spending habits, based only on patterns in their features. These groupings are suggestions, and it is up to you to interpret what each cluster means. This makes clustering more exploratory, as you analyze the discovered groups to understand the structure of the data. In clustering, there is no target column, so the analyst plays a creative role in deciding which features to use, how to scale them, and how many clusters to form. Different choices can lead to different but still valid groupings, such as hospitals finding patterns in patient data, or traffic agencies detecting congestion trends. The value of clustering lies in how these groupings improve understanding and support decisions. This lack of predefined labels is not a weakness, but a strength that allows clustering to reveal hidden structure in the data. Similarity-based groups. Clustering is a method for grouping items based on how similar their characteristics are, such as grouping customers by age and income, patients by health measures, or songs by tempo and genre. Each item is treated as a point in a space defined by its features, and clustering brings together points that lie close to one another. Instead of using predefined labels, it relies on patterns in the feature values so that natural groupings emerge directly from the data. Imagine plotting fruits in a three-dimensional space using features like weight, sweetness, and color intensity. In this space, similar fruits naturally form clusters, such as groups of apples or groups of oranges. A clustering algorithm finds these dense regions of similar points without needing labels that say which fruit is which. This lets the structure of the data itself reveal natural groupings, showing which examples belong together based on their shared characteristics. Clustering is a technique for discovering hidden patterns by grouping data points that share similar features. For instance, in a dataset of online learners, it can reveal groups such as highly engaged users and sporadic visitors by examining behaviors like login frequency, video views, quiz completion speed, and forum activity. These groups form naturally based on similarities in their feature values, without needing predefined labels. As a result, clustering organizes complex data into clearer structures and uncovers insights that are not immediately obvious. Clustering for exploration. Clustering is an exploratory technique that lets data reveal its own structure by grouping similar examples based on their features. It is especially useful in new or complex domains where patterns are not obvious. By forming these groups, clustering exposes natural segments and behaviors that are hard to see in raw data. This provides a clear view of hidden structure and a helpful starting point for deeper analysis before defining specific predictive tasks. Clustering is useful in many real-world situations because it groups similar cases to reveal meaningful patterns. For example, a public health researcher can cluster neighborhoods by age, income, and healthcare access to find communities that may need more clinics. And a museum can cluster visitors by which galleries they see and whether they use guides to identify different visitor types. These clusters are not final answers, but starting points that help researchers and organizations ask deeper questions about why these groups exist and how to better serve their needs. Clustering supports a reflective way of analyzing data by letting us form and then refine groups based on feature values. We can change which features we use, how we measure similarity, or how many clusters we create, and then observe how the groupings shift. For example, an environmental scientist might cluster lakes by their characteristics and use the resulting groups to generate new ideas about pollution or ecosystem health. In this way, clustering drives an ongoing cycle of discovery, where we interpret patterns in context and gradually deepen our understanding of the data and the phenomena behind it. Distance and similarity. Point-to-point distance. In clustering, we represent each example as a point in a multidimensional space where each feature, such as age or income, is one axis. We then measure numerical distances between these points to see how close or far apart they are. Points that are close together have similar characteristics and tend to form clusters, while points that are far apart belong to different groups. By examining these distances, we can discover natural groupings in the data and identify examples that stand out as outliers. In clustering, distance is a way to measure how similar items are to each other. For example, a music streaming service represents each song with features like tempo and loudness, and songs with similar features end up close together, while very different songs are farther apart. Using these distances, algorithms can group songs into clusters, such as relaxing playlists or intense workout mixes. In this way, point-to-point distance is the main tool for forming groups of similar items. The distance between points depends on which features we choose and how we measure differences in those features. In a healthcare example, patients might be compared using blood pressure, heart rate, and cholesterol levels. Patients with similar values across these features are close together in the feature space and may belong to the same risk group, while a large difference in one feature, such as blood pressure, increases their distance and suggests they belong to different clusters. By examining these distances for many patients, we can identify clusters where points are tightly grouped and separated from other patterns by larger gaps. Python code, point-to-point distance. This script demonstrates how to calculate distances between points to measure how similar they are. It represents customers with small numeric feature vectors and then compares them by computing the distance between these vectors. The key idea is that smaller distances indicate greater similarity between customers. As you listen, focus on how these distance values capture and reflect similarity between different examples. The script starts by importing the math library so it can use built-in mathematical functions. This is especially important for calculating square roots, which are needed to find the Euclidean distance between points. Using the math library ensures these distance calculations are accurate and efficient by relying on Python's optimized tools for math operations. We represent two customers, Alice and Bob, using dictionaries that store their names and a tuple of numeric features. For Alice, the features are an age of 25 and 5 products purchased. For Bob, the features are an age of 27 and 6 products purchased. Organizing the data this way makes it easy to compare the customers based on their numeric attributes. We now introduce a third customer, Kara, whose information is represented as a pair of numbers, 40 for her age and 1 for the number of products she has purchased. She is chosen to be more different from the other customers, so we can better see how the distance calculation works. By comparing her features to those of the others, we can observe how larger distances indicate greater dissimilarity between customers. We define a function to compute the Euclidean distance between 2 points by first unpacking their coordinates. From each point's feature tuple, we extract the first value as the x-coordinate and the second value as the y-coordinate. Separating these components makes it possible to perform the distance calculation using the individual x and y values. This setup prepares the data so the distance between the 2 points can be computed correctly. The code computes the sum of squared differences between 2 points. It subtracts the x-coordinates, squares that result, and does the same for the y-coordinates. These squared values are then added together to give a single number. This number represents the total squared difference across all features and is used to determine the Euclidean distance between the 2 points. The function computes the Euclidean distance between 2 points by taking the square root of the sum of the squared differences. This final step turns the squared sum into an actual distance value. It uses the square root operation from the math library to produce a meaningful measure of how far apart the 2 points are. We create a list of customers where each customer is represented by a small dictionary containing their name and a pair of features, their age, and how many products they have purchased. Organizing the data this way makes it easy to loop through all customers and work with their information. In particular, we can treat each pair of features as a simple feature vector and compute distances between customers to analyze how similar they are. The code prints a short header to explain what the features in the calculations represent. It clarifies that one feature is age in years and the other is the number of products purchased. This description provides context for interpreting the data. As a result, anyone reading the output can understand what the numbers in the feature vectors mean and how to compare them correctly. We use a loop to go through the list of customers one at a time. In each pass of the loop, we treat the current customer as the first member of a pair. This lets us systematically compare that customer with the others in the list. By doing this for every customer, we can calculate distances for all unique customer pairs without repeating any comparisons. The loop goes through the list of customers, starting from the one after the current customer, so that each pair of customers is checked only once. This approach prevents repeating the same comparison in reverse order. As it iterates, it picks the next customer to pair with the current one. This prepares each unique pair for a distance calculation in an efficient way. We use a helper function called Euclidean distance to measure how far apart 2 customers are based on their features. It takes the feature values of the first and second customers, here their age and number of products purchased, and compares the differences between them. From these differences, it calculates a single numerical distance value. A smaller distance means the customers are more similar, while a larger distance means they are more different. We display a summary of the distance between 2 customers, showing the name of the first customer, the name of the second customer, and the computed distance between them. This distance value is formatted to 2 decimal places for clarity. Presenting it this way makes it easier to compare how similar or different the customers are based on their features. The code finishes by explaining how to interpret the distance values it computed between customers. It states that a smaller distance means 2 customers are more similar overall. This interpretation connects back to the earlier calculations and reinforces that Euclidean distance is being used as a measure of similarity between their feature vectors. This script computes the Euclidean distance between 3 customers using their age and number of products purchased as features. It applies a simple distance function to measure how similar or different each pair of customers is. When you run it, the script prints the distances between all pairs, showing that Alice and Bob, who have more similar features, are closer together than Kara, who was chosen to be more different. The key idea is that a smaller distance value means the customers are more similar based on the features used. Scaling and distance. When we group examples using distance, the scale of each feature matters a lot. Distance measures are sensitive to the size of the numbers, so a feature with large values can dominate and drown out another feature with smaller values. For instance, when clustering customers by income and satisfaction, income differences can overshadow satisfaction because income is on a much larger scale. As a result, the clustering may reflect mostly income and ignore important satisfaction information. To avoid this, we rescale features so that differences in each one have a similar influence on the distance calculation. When we calculate distances between data points, we often rescale or normalize the features so they are on a similar scale. This prevents one feature from dominating the result just because it has larger numerical values. For instance, income and satisfaction scores can be adjusted based on how far they are from their averages so they contribute more equally. Doing this helps clustering methods form more balanced groups that reflect both economic and subjective factors, instead of being driven mainly by the feature with the biggest numbers. When working with different kinds of data, such as health measurements, scaling is important so that no single feature dominates just because it has larger numbers. If we skip scaling, clustering methods may focus mostly on the feature with the biggest range, which can distort the results. By adjusting the scales, we can balance the influence of each feature or intentionally give more weight to the most relevant ones. This makes our distance calculations better reflect the true similarities we care about, instead of being driven by arbitrary units. Python code, scaling, and distance. This script demonstrates how scaling features changes the distances between customers. It compares distances computed from the original features with distances computed after scaling. The focus is on how much the income feature and the satisfaction feature each contribute to these distance values. We start by importing the NumPy library, which lets us handle numerical operations and work efficiently with arrays. We also import the pyplot module from matplotlib, a tool for creating visualizations in Python. In this script, we use pyplot to generate plots that show how distances change before and after we scale the data. Together, these libraries allow us to both compute and visually compare the effects of scaling. We set a fixed random seed in the NumPy library using the value 42 so that any random numbers generated will be the same each time the code runs. This makes the results reproducible, meaning you can reliably repeat experiments or analyses. It is especially helpful for debugging and for comparing outcomes across different runs of the script. We create a small synthetic customer dataset as a two-dimensional array where each row represents one customer and each column represents a feature. The two features are income, measured in dollars, and a satisfaction score. The four customers have incomes of $20,000, $50,000, $80,000, and $120,000, with satisfaction scores of 2, 4, 3, and 5. The values are stored as floating point numbers to maintain numerical precision for later calculations. We begin by printing a short message that explains the structure of our customer data, noting that it includes income in dollars and a satisfaction score. This message provides context for what the data represents. We then print the actual customer data array, so we can see the income and satisfaction values for each customer. Viewing this output lets us quickly verify the data before performing any further calculations or transformations. This function computes the Euclidean distance between 2 points represented as arrays. It first subtracts one array from the other to get the difference for each corresponding element. Then it squares these differences, adds them together, and takes the square root of that sum. The result is a single floating point value that measures how far apart the 2 points are in the feature space. This operation computes the Euclidean distance between 2 points. It does this by finding the squared difference along each dimension, adding these squared values together, and then taking the square root of that sum. The final distance is returned as a floating point number to keep numerical results consistent. We begin by choosing a single customer as our reference point for distance calculations, using the first customer in the dataset. We extract this customer's features and store them so they serve as a consistent baseline. All other customers will then be compared to this reference to measure how far they are in terms of their features. This approach lets us evaluate distances in both their original form and in scaled form later in the analysis. We begin by creating an empty list to hold distances from a chosen reference customer. Then we go through each customer in the dataset and use the Euclidean distance function to measure how far that customer is from the reference based on their feature values. Each calculated distance is added to the list. In the end, this list shows how similar or different every customer is from the reference in terms of their raw features. We convert the list of raw distances into a NumPy array so we can use NumPy's fast and efficient array operations for later calculations. By setting the data type to float, we store all distances as floating point numbers. This choice improves numerical precision and reliability when performing computations on these values. We start by finding the mean of each feature across all customers, such as the average income and the average satisfaction score, and use these as reference points. Then we calculate the standard deviation for each feature to measure how much individual values vary around their means. Using these statistics, we transform the data so that each feature has a mean of 0 and a standard deviation of 1. This standardization is a common pre-processing step that helps ensure each feature contributes equally to distance-based calculations. To avoid division by 0 when scaling features, we adjust the array of feature standard deviations before dividing. We use a check on each standard deviation value, and if any value is 0, we replace it with 1. All non-zero standard deviations are left unchanged. This guarantees that the division step in feature scaling is always safe, while still producing features with 0 mean and unit variance wherever possible. We scale the customer features so they have a mean of 0 and a standard deviation of 1. To do this, we subtract the average value of each feature from its data points and then divide by that feature's standard deviation. This standardization puts different types of features, such as income and satisfaction scores, on a comparable scale. It is important because many machine learning algorithms work better and more reliably when the input features are standardized in this way. We begin by choosing the same reference customer as before, but now from the scaled data, so that distance comparisons remain consistent. We then create an empty list to store distances from this reference. For each customer in the scaled dataset, we compute the Euclidean distance to the reference using the scaled features and add this value to the list. By doing this for all customers, we can see how scaling changes the distances between customers. The code turns the list of scaled distances into a NumPy array so that numerical operations can be done more efficiently. This conversion also makes sure all values share a consistent data type using floating point numbers for better precision. Using the NumPy array structure is important because it allows later calculations and analyses to take advantage of NumPy's optimized performance. We first print a message to indicate that we are about to show the raw distances from the reference customer, labeled as customer 0, so we can see how far each customer is in the original feature space. Then we display the array of these raw distances. Next, we print a message to introduce the scaled distances, which are computed after standardizing the features. Finally, we show the array of scaled distances so we can compare how standardization changes the measured distances between customers. We use a function from the NumPy library to create a sequence of index values, one for each customer in the dataset. These index values define the horizontal positions of the bars in the bar plot. By assigning each customer to one of these positions, we can clearly display and compare their distances on the chart. We begin by choosing a bar width of 0.35, which controls how wide each bar appears in the chart. Then we create a new plotting figure with a size of 6 by 4 inches. This figure acts as the canvas for our bar plot, where we will visually compare the distances before and after scaling. We use matplotlib to create a bar plot that shows the raw distances as bars on the left side. The x positions of these bars are set using an index array, and we shift these positions by half the bar width, so the bars are properly aligned. A single bar width value controls the size of all bars to keep them consistent. These bars are labeled as raw to distinguish them from other data in the same plot. This line creates a bar chart in matplotlib for the scaled distances and places these bars slightly to the right of the original distance bars by shifting their positions by half the bar width. Each bar uses the same predefined width. The bars are labeled as scaled, so the legend can clearly distinguish them from the raw distance bars. We label the horizontal axis as customer index to show each customer's position in the dataset, and the vertical axis as distance from customer 0 to indicate how far each customer is from the reference customer. The plot title, Effect of Feature Scaling on Distance Values, explains that the figure compares these distances before and after scaling the features. Together, these labels and the title make it clear that the goal is to show how feature scaling changes the computed distances between customers. We add a legend to the plot, so listeners can distinguish between the bars for raw distances and scaled distances. We then adjust the layout so all elements fit neatly without overlapping or being cut off. These steps make the final plot clearer, easier to interpret, and more professional before it is displayed. At the end of the script, a plotting function from the visualization library is called to display the graph. This step actually renders the chart that compares the raw distances with the scaled distances. By viewing this plot, we can clearly observe how feature scaling changes the distance values between customers. This visual comparison helps us understand the impact of scaling on distance-based analysis. This script shows how scaling features changes distance calculations between customers based on income and satisfaction scores. It first computes Euclidean distances from a reference customer using the original values, then rescales the features to have zero mean and unit variance, and computes the distances again. The comparison reveals that the distances change substantially after scaling, which can be seen in a bar plot of raw versus scaled distances. This demonstrates that feature scaling is crucial in distance-based analyses so that no single feature dominates the results simply because it is measured on a larger scale. Visual 2D examples. Imagine each customer as a point on a two-dimensional map, placed according to how much they spend on groceries and entertainment. Points that lie close together represent customers with similar spending habits and are likely to belong to the same cluster. Points that are far away from most others suggest different behavior and may form a separate cluster or be outliers. By looking at how these points group or stand apart, you can visually identify which customers should be grouped together based on their distances. Imagine each student as a point on a graph placed according to their math and writing scores. Points naturally form clusters, such as groups of students who are strong in both subjects or weak in both, and groups that show strength in one subject but not the other. Distance-based reasoning assigns a student to a cluster by checking which nearby points they are closest to. If a student lies between groups, you compare their distance to the center of each cluster to decide where they most naturally belong. Imagine plotting restaurants on a map, where one axis is price and the other is customer rating, and noticing that points naturally form clusters. By starting with one restaurant and looking at its closest neighbors, you can mentally draw circles around nearby points to form small groups of similar restaurants. As you expand these circles, you see gaps where there are few or no points, which mark natural separations between clusters. This visual process shows how grouping by proximity in a two-dimensional space can reveal meaningful clusters in the data. Python code, visual 2D examples. This script demonstrates simple two-dimensional clustering based on distance between points. It visualizes how points that are close together naturally form groups in a scatter plot. By watching these clusters appear, you can better connect the abstract idea of distance with concrete, realistic-looking data patterns. A line that begins with an exclamation mark is used as a command to install required Python libraries, in this case NumPy, matplotlib, and Seaborn. It is commonly used in environments such as Jupyter Notebooks. The purpose of this command is to make sure these libraries are installed and available before the rest of the code runs. This preparatory step helps prevent errors that would occur if the necessary dependencies were missing. We begin by importing the numerical library that efficiently handles large, multi-dimensional arrays and provides many mathematical functions for working with numerical data. We also import the plotting module from the visualization library, which lets us create static, interactive, and animated graphs. Using this plotting tool, we can generate visual representations of our data, such as scatter plots, to help us see how points cluster based on their distances. We set a fixed random seed using a numerical library so that any random numbers generated later in the script are always the same each time the code runs. This makes the random points reproducible instead of changing on every execution. Reproducibility is important because it allows us to debug more easily and share results that others can reliably repeat. We define 3 cluster centers to represent different spending patterns on groceries and entertainment. Each center is a pair of numbers in a two-dimensional space, where the first value is grocery spending and the second is entertainment spending. These centers act as reference points that describe typical spending behaviors. Later, we can generate data points around these centers to simulate how different people might spend in these two categories. We begin by creating an empty collection to store our spending points. For each predefined spending center, we generate a small cluster of points by adding random noise drawn from a normal distribution with mean 0 and standard deviation 5. This process produces 15 points around each center, forming a cloud of nearby values. We then add each cloud to our collection, gradually building the full dataset used for visualization. The code combines all the separate arrays of spending points, which were created around different cluster centers, into one larger array. It does this using a vertical stacking function from the numerical library, which merges the smaller arrays into a single structure. Once combined, this unified array can be plotted, making it possible to display all the spending points together in one scatter plot. We represent the cluster centers for math and writing exam scores as 4 coordinate pairs in a two-dimensional space. Each pair gives a typical combination of math and writing scores, acting as a central point for a group of students. These centers are chosen to simulate different performance groupings. Using them makes it easier to visualize how students might naturally cluster based on their scores in the two subjects. We create a dataset of exam scores by first setting up an empty list to hold groups of points. For each exam center, we generate a small cloud of points by adding random noise to the center's coordinates using a normal distribution with mean 0 and a standard deviation of 4. This produces 10 two-dimensional points clustered around each center. Each cloud is then added to the list, building up the full collection of simulated exam score data. The code combines all the exam score points into one array so they can be plotted together. It does this by stacking the separate groups of points that were created around each cluster center into a single dataset. This unified set of points is then used to make a scatter plot. As a result, we can clearly see how the exam scores are distributed and how they form clusters. We begin by choosing one specific grocery customer and one specific student for closer analysis. In our data, we select the 6th customer and the 13th student based on 0 starting index positions. These chosen individuals serve as reference points so we can examine and compare how far they are in terms of data features from others in their respective groups. This setup helps us highlight and interpret distance relationships within each dataset. We can isolate a single customer's spending data by taking the entry at that customer's index from the spending array. And we do the same for a student by using the student's index in the exam scores array. This gives us the specific data points for the customer and the student. Once we have these selected individuals, we can focus our analysis on them, such as computing distances between their points and others in the dataset. To find the Euclidean distance from one chosen customer to all others, we compare their coordinates. For each customer, we subtract the reference customer's coordinates from that customer's coordinates to get the difference in each dimension. We then square these differences, add them up, and take the square root of the result. Doing this for every customer gives an array where each value is the distance from the reference customer to another customer. We are finding how similar each student is to a chosen reference student by computing Euclidean distance between their exam scores. For each student, we subtract the reference student's score on each exam, square these differences so they are all positive, and add them up. Then we take the square root of this sum. The result is a single number that tells us how far each student's performance is from the reference student's performance. To find the 3 nearest neighbors for a customer, we start by sorting all distances from that customer to every other customer. We use a function that returns the positions of the distances in sorted order, rather than sorting the distances themselves. From this ordered list, we take the indices of the 3 smallest distances, skipping the first one, because it corresponds to the customer's distance to itself. The remaining 3 indices identify the customers whose spending patterns are most similar to the chosen customer. To find the 3 nearest neighbors for a student, we start by sorting all distances from that student to every other student in ascending order so the closest ones come first. After sorting, we ignore the first entry because it represents the student's distance to themselves. We then take the next 3 entries in the sorted list, which correspond to the 3 closest other students. These positions give us the indices of the student's nearest neighbors. The code prints a summary of the nearest neighbor distances for both customers and students. It first computes the distances from the selected customer to its nearest neighbors and rounds these values to 2 decimal places to keep the output clear and readable. It then repeats this process for the selected student, again rounding the distances. Overall, this produces a concise, easy-to-interpret view of how close the nearest neighbors are to each chosen reference point in the 2 datasets. We create a figure that shows 2 scatter plots side by side by using a subplots function with 1 row and 2 columns. The figure size is set to 10 by 4 inches, so the plots are large and easy to see. This layout lets us place 2 different datasets in the same figure and compare them visually. In the first subplot, we focus on customer spending patterns by creating a scatter plot of all customers. Each point shows a customer's grocery and entertainment spending. These points are drawn in light gray to indicate they are background data rather than the main focus. We label this group as other customers so the legend can clearly distinguish them from any highlighted groups in the visualization. Here we highlight a specific customer on the scatter plot by drawing a single point in red with an X-shaped marker. The marker is made larger for better visibility. We also assign it the label chosen customer so it can be clearly identified in the plot legend. This line creates a scatter plot in matplotlib that highlights the nearest neighbor customers. It selects their coordinates from the full set of points and plots them with blue circular markers. The markers are made larger for better visibility, and a label is added so these highlighted customers appear clearly identified in the plot legend. The code labels the horizontal axis as grocery spending per month and the vertical axis as entertainment spending per month, so listeners know what each axis represents. It then gives the subplot a title that explains the data shows customers grouped by similar spending patterns. Finally, it adds a legend in an automatically chosen position to identify the different groups or points in the scatter plot. In this part of the code, we work with the second subplot, which is used to display exam scores. We select the second axis from the subplot layout and create a scatter plot of all the exam data points. Each point shows one student's math score and writing score. The points are drawn in light gray to indicate they represent the general group of students, and they are labeled as other students in the legend for clarity. Here, we use matplotlib to plot one student's exam scores as a scatter point and make it stand out. We color this student's point red, use an X-shaped marker, and increase its size for better visibility. We also assign it the label chosen student so it appears clearly identified in the plot legend. In this step, we plot the nearest neighbor students on the scatter plot using a standard scatter plotting function. We take their x and y coordinates from the exam points array, using the indices that identify the closest students to our reference student. These nearest neighbors are shown as green circles with a larger marker size for better visibility. We also assign them the label nearest neighbors so they can be clearly identified in the plot legend. We label the horizontal axis as math exam score and the vertical axis as writing exam score, so it is clear what each direction represents. The plot title, Students Grouped by Similar Exam Performance, explains that the scatter plot shows clusters of students based on their scores. We also add a legend, placed automatically in the best position, so listeners can distinguish the different groups or points in the plot. The code first uses a tight layout function from matplotlib to automatically adjust the positions and spacing of the subplots so they fit neatly within the figure window. This step helps prevent overlapping labels or elements and ensures the plots are clearly visible. After the layout is adjusted, the code calls the show function from matplotlib to render and display the figure on the screen for visualization. This script demonstrates two-dimensional clustering by creating scatter plots for spending patterns and exam scores. It generates clusters of points around set centers using random variation to mimic real data. In the spending example, clusters represent grocery and entertainment expenses, and in the exam example, they represent math and writing scores. For each plot, the script highlights one chosen point, finds its three nearest neighbors using Euclidean distance, and prints those distances. The visual result shows how points that are close together can be grouped into clusters based on their proximity. Making sense of clusters. Cluster summaries. After forming clusters, the next step is to summarize each group by describing its main characteristics rather than individual cases. You do this by looking for central tendencies, such as typical averages or common behaviors, and then expressing them in clear, everyday language. For instance, a cluster of customers who often make small online purchases and rarely use discounts can be described as regular online shoppers who buy frequently but spend modest amounts each time. The goal is to turn raw data into a simple, meaningful narrative that clearly defines each group and makes the results easy to understand and use. When summarizing clusters, focus on what makes each group distinct rather than only describing shared traits. Highlight standout features such as extreme values or unusual combinations of characteristics. For instance, one group of cities might have clean air and many parks, while another faces pollution and heavy traffic. Labeling these as transit-oriented greener cities versus car-dependent cities under environmental stress makes the differences clear. This way of describing clusters shows why the grouping is useful and how the clusters meaningfully differ from one another. Cluster summaries are most useful when they match the goals of your analysis, not just technical patterns. The same data can mean different things to different roles, such as a marketer, educator, or healthcare provider. For example, students with high attendance but low participation might be described as physically present but passively engaged, while patients with moderate risk but poor follow-up might be seen as reachable but not adherent. Framing clusters this way turns statistical patterns into clear, actionable insights for decision-makers. Labeling cluster groups. After forming clusters, the next step is to assign each group a short, human-friendly label that reflects its main characteristics. This step relies on human judgment rather than full automation because it involves translating numerical patterns into real-world concepts. You examine which features are high or low in each cluster and summarize these patterns in a clear descriptive phrase. The goal is to choose labels that make it easy for someone unfamiliar with the data to quickly understand what each cluster represents. When labeling clusters, focus on what makes each group distinct compared with the others. For example, in healthcare, you might group patients by age, activity level, and health markers, leading to one cluster of younger, active, healthy adults and another of older patients with higher risk factors and more sedentary lifestyles. Instead of vague labels like Cluster 1 and Cluster 2, you would name them in a way that reflects these differences, such as low-risk, health-conscious adults and older, high-risk sedentary patients. Clear descriptive labels make the clusters easier to interpret and more useful for decision-making. When labeling clusters, it is important to avoid bias and base labels only on what the data actually shows. Labels should describe observable patterns, not assume underlying causes, or make value judgments about people or places. For example, instead of calling students with late submissions unmotivated, describe them as having irregular engagement patterns. And instead of assuming areas with high public transit use are low income, simply describe them as transit reliant unless income data confirms otherwise. By focusing on measurable traits and consulting domain experts, cluster labels can support interpretation and decision-making without reinforcing stereotypes. Applying clusters to decisions. Once you have identified and interpreted clusters, the main value comes from using them to guide decisions. You treat each cluster as a distinct group with its own tendencies or risks, and adjust your actions to match. For example, in healthcare, a cluster of patients with moderate age and high blood pressure might receive targeted prevention programs and more frequent check-ins, while younger, healthier patients receive standard visits and digital reminders. This lets you allocate resources more efficiently and replace one-size-fits-all strategies with more nuanced, evidence-based decisions. When using clusters to guide decisions, focus on what actions are both impactful and feasible for each group. For example, A retailer might cluster customers into loyal premium buyers, occasional bargain hunters, and new customers, then offer early access to the loyal group, targeted promotions to bargain hunters, and onboarding support to new customers. Any decisions based on clusters should remain ethical and practical, avoiding harmful practices like withholding essential services or over-tailoring to very small segments. The key is to balance personalization with fairness and operational constraints so that clustering leads to effective and responsible actions. When using clusters for decision-making, treat them as hypotheses rather than absolute truths. Clusters show groups of examples with similar behavior, but not every member will respond the same way to an action. For example, a city might group neighborhoods by crime and resources to guide where to send more support. Because conditions change, decisions based on clustering should include ongoing monitoring, feedback, and regular updates. This makes clustering a dynamic tool that supports informed choices in many different contexts. In this lecture, you learned to describe clustering as grouping similar examples based on feature values. Use simple distance-based reasoning to decide which examples belong together, and interpret clusters in terms of meaningful patterns in a given context. In the next lecture, Lecture B, we will go over simplifying features. Thank you for your attention. See you all in the next lecture.